Hey, let me introduce the next talk. So our next speaker is Thorsten Altenkirch. He is from University of Leipzig, and he will speak about the syntax for cubical types.
Okay, thank you, and thank you for inviting me. First, apology, though I submitted an abstract in the hope I would have something to say about the content of the abstract, but I feel that this is not sufficiently the case, so I went back to another topic. And next apology, some people may have seen me talking about this already in Paris or on YouTube.
Oh, I saw it on YouTube.
You saw on YouTube.
Yeah, I think it was very nice.
I watched that.
Okay.
It was the kittens.
Maybe I should just replay. Maybe the next thing is I play it. Okay, no.
Or the comments on YouTube.
Then you can join the audience and just comment.
Yeah.
Can we play YouTube now?
Yeah, sure. Also to increase the excitement, the more difficult part of the talk is going to be given by Ambrus sitting there. So I'm just doing the easy introduction. Let's see what that's easy. And then when it gets a bit hairy, he's going to take over. That's how we do it. Okay. I would like to say something which I find quite important. So to me, what's called homotopy type theory is really what I find most interesting is that it introduces a very strong principle of extensionality. So so far, I mean, we have been thinking about extensionality for functions. So if two functions are pointwise equal, then they should be equal, which was an issue in type theory. But now we have an even stronger principle, namely that two structures which are equivalent we can consider as equal. And I think using extensionality gives us lots of opportunities for abstraction. It enables us to do mathematics or also verification in a very layered way, to abstract away from details of implementation. So, and it is type theory which enables this, because type theory, as a fundamental philosophy, it doesn't assume that there is a given sort of universe of objects which we not all have to solve, which is sort of the idea in set theory. But instead, when we introduce types and elements at the same time. So we can never talk of an element in isolation. And this inability is something actually we never should do, really. And this inability enables us to postulate this very strong extensionality principle, because we cannot observe any intentional structure of objects in type theory. Hence, we can say that two objects which are extensionally equivalent, which behave the same, are equal. And this is an opportunity which is enabled by type theory. On the other hand, in type theory, a very important idea is this computational character of type theory, that we can compute things. And there is a problem, but it's very easy to understand how we can compute with natural numbers and simple objects we know in type theory. When we move to objects like functions and universes and add these extensionality principles, it's not clear how we can extend this computational character of type theory to these extensionality principles. And that to me seems to be a very, very central problem. So that's the goal. So in homotopy type theory we have this univalence axiom. So like if we know, if we have an isomorphism, like from bool to bool using negation, yeah, then we know that bool is equal to bool, or two types which are isomorphic, let's say, or equivalent, are equal. So this is this extensionality principle, and it forces us, I mean, if we want to have this sort of extensionality, it forces us to give up this idea of uniqueness of equality proofs, because we cannot have this sort of extensionality and at the same time have uniqueness of equality proofs. But the real issue is now, how do we compute this principle? So for example, in type theory, we can write this function, coerce, if A is equal to B, then we have a function from A to B. And in ACTA, you would write this by pattern matching, say, okay, the only proof of equality is level, hence I only have to implement this for the identity function. But this is not true anymore, because now we allow other proofs of equality, like proofs which are generated by this univalence principle. And even though maybe if you look at this, it may appear, okay, if E is just a proof of the form above, then we just use the function which is in this, which we have used to prove this equivalence. So it seems to be okay, there should be a way to compute with this principle, but it is actually more complicated, because there may be other ways how we have derived this equality, and we have to be able to compute with all these ways to arrive this equality A equals B, and that turns out to be quite difficult. So adding univalence naively to type theory disables this computational understanding of type theory, or seems to disable it. So our goal here is to define a type theory where we have univalence. So univalence is maybe not an axiom, but it's something which is admissible. But on the other hand, every closed term of type bool and other types computes to some value, in the case of bool to true or false. Okay. So that's the goal here. So the plan of action is to observe that maybe the sort of fundamental error in intentional type theory is to have this sort of idea of that equality is defined inductively by reflexivity being the only constructor, and instead to say equality can really be defined by recursion over the type. So for example, here equality over natural numbers is simply a recursive So equality of the natural number is simply a recursive function which returns either the empty set or a unit. Equality of pairs is equality for both components, right? Equality of functions, extensional equality, and then equality for types is exactly this univalent equivalence here between this.
But doesn't the right-hand side of the bottom line, A equivalent to B, presuppose that you know what equals means for A and B?
Yes, but I know what equal means for A or B because I have defined recursively for all types.
Well, A and B are just elements of U.
Yeah.
Well, they might be variables.
Yeah, they're variables. So at the moment I'm stuck, but as soon as I instantiate these variables, I can compute the equality. So I mean it's like this. If I write plus x plus y, yeah, then you don't know what x plus y is, you know, but as soon as you instantiate x and y, you can compute. So it's the same situation here.
Okay.
Yeah? So equality is now a non-canonical constant, which as soon as I instantiate the type, computes to some other type. Yeah? And so all the type formats I've used are expressed previously. For example, I have products and functions and so on. Yeah? Okay. So the idea is now that we start with model of type theory without the identity type, and now introduce identity type by recursion of the type formats as shown there. It's a very simple idea. And this talk will try to make this idea more precise. And I would like to say some words about the previous work, starting with some work of myself and Conor McBride and Walter Scherstner, which was based on some earlier work, where we defined something which is called observational type theory. And at this point in time, we lived in the pre-homotopy period of type theory, but we didn't think about this. But we wanted to have some notion of extensionality for functions. And this is something already which you cannot prove in intentional type theory. And if you add it, you destroy the computational character, exactly for the reasons I've shown before. So we were using the so-called setoid interpretation of type theory to define a translation of type theory, which then enables us to interpret extensionality. And this work essentially relies on this uniqueness of a very strong form of uniqueness of identity proofs. And the reason why it does this, I think, is mainly because the way we defined the heterogeneous equality, which plays a very important role in this construction. So this work, it wasn't possible to extend it to a homotopy situation because it relied on this uniqueness of equality proofs. And if you look on how it worked, it uses this idea of a setoid model, where every type is modeled as a type together with a propositional equivalence relation. So it was relying essentially on this propositionality at this point. But otherwise, it worked like I just sketched. It defined types by recursion, equality by recursion over types, and hence was able to interpret extensionality. But it wouldn't be possible to extend this to univalence, exactly because it relied on UIP. Now, to move on, and I tried for a while to see how we could do this in a proof-relevant context. And then some interesting, important inspiration came by work a number of people, somehow most of them from Gothenburg. There's this work by Bernardi and Johnson and Patterson on parametricity, and later Bernardi and Moulin about computational interpretation of parametricity. So what is parametricity? The parametricity is an idea to define relations, a relation between types, by recursion over types. So that's what came up when we defined equality. And then you want to show a certain property which enables us to show that functions will never look at the types. They're sort of uniform or parametric. This is a notion which was introduced by Reynolds to show that functions, polymorphic functions, are representation independent. And there we use these logical relations defined by recursion over types. And some other important work is this work by Bizan, Coupon, and Huber on the cubical set model of type theory, which is the first of constructive model of homotopy type theory. And it turns out that if you look close enough at this parametricity interpretation, it turns out that the cubes showing up in a natural way. So what we want to do is to combine these two ideas, this idea of parametricity, which is sort of very syntactic, and this model construction, and extend this idea to define equality by recursion over types to homotopy type theory. Okay. So, first essential idea is to introduce a notion of heterogeneous equality. So, what I showed before, I only gave interpretation of equality for sort of simple type constructors like products and pairs. But when we move into dependent types, we need to be a little bit more sophisticated. So, for example, if I want to define equality for elements of a sigma type, we here use the sigma type of natural numbers and vectors of size I, which are also called lists, by the way. And if I have two pairs, and I want to say when are these two pairs equal, then the equality again is a sigma type. The first component, the natural numbers, have to be equal, and the second component has to be equal. But the problem is that the second component, the two elements don't have the same type. X's is a vector of length m, and y's is a vector of length n. That means we compare things in different types, but this is justified by this assumption of this equality R that the two numbers are equal. So we have to introduce a notion of equality which allows us to compare elements in different types where we have a proof that these types are equal again. Okay? That's the notion of heterogeneous equality. So which basically says that if we, to compare vectors of size m and size n, we use this assumption that m is equal to n, and hence down here we annotate this equality. This is proof that these two types, the elements of these two types, are actually propositionally equal again. So what we do is we want to define an equality, the equality tilde A, which is between two different types, which I call here A0 and A1. And 0 and 1 are projections which are defined in this context gamma equal. So where gamma equal is a context which for every type in gamma introduces two assumptions and the assumption that these two elements are equal. So that's what's given down here. If I have an assumption, what do I do this? That's something. Is it cleaning? Oh, it's a cleaning instrument. Well, that's very good. Okay, so
there's a pointer which might have a laser there.
it's a pointer which may have a laser.
How is it?
No. Okay.
There also may be a mechanical point.
Yeah, that's good. That's good if I find one.
Well,
There's this cleaning instrument, but it seems a bit violent to use this.
yeah.
It's a bit big.
It's that thing behind your fingers that you could use.
I have one here, I don't know whether it's long enough, but
I'm not sure you got it.
you were told.
Okay. So what I say here is this definition of this context gamma equal. If I have an assumption x colon A, it's getting tripled into assumption x0 A, but this may again be a different type because this equality may depend on the assumption made earlier, and an element x1, which is an A of 1, and then the assumption that these two elements are heterogeneously equal. So at the same time, I introduce this context, gamma equal, the equality, this heterogeneous equality, and these projections. So the projections are thus defined very simply, just project out this xi. So 0 projects out x0, and x1 projects out x1. So what we have is, we have gamma equal, and we have these two projections, 0 and 1, going down. And now this heterogeneous equality can be defined as indicated before by recursion over the types, but it also works for dependent types. So for pi types, I assume a triple here, which is related, and for sigma types, to say when two elements of a sigma types are equal, I assume that the first components are equal, and then for this equality B, I need an extended context which gives me some value for x0, some value for x1, and x2 is done this equality. So that's a very, very natural generalization of what we had seen for simple types. First, what is the equality?
Sorry, first,
Yeah?
may I interrupt you?
Sure.
May I start interrupting the issues?
Yeah. I like to get interrupted. I feel a bit lonely if I don't get interrupted.
So do I actually when I give a talk. When you read this B tilde subscript capital B square bracket x0,
Yeah, so tilde b,
that means, yeah, so that B is equal to B prime in that extended context.
yeah, so b is an element of u in this context, right? So now in gamma equal x0 in a0, x1 in a1,
Actually, if you could,
x2 in x0 equal to x1, I have this, what is it, b equal in b to b prime.
wait, what is
Well,
X?
no, that's not that. Tilde b is now b0 b1 to the u, right?
Wait, let X2 in A. Okay.
And what I now do here, I define the substitution from, from gamma equal into this context where x0 is a, right? x1 is, what was it? A prime, and x2 is what's called x2.
I thought that subscript on the tilde was going to be an equality proof.
So,
I thought the subscript on the tilde would be an equality proof, but you wrote
the
it
subscript, that was,
You had tildes
different
at B on the
notation.
previous
yeah, it was a
slide.
different, okay, just to confuse everybody, I'm changing notation, you know. This is just a substitution. The tilde b is just the relation, the equality proof is now in the context, yeah. So equality which proves now that these arguments are equal are just part of the context.
What context is B living in?
Here, b lives in the context gamma x colon a. Okay? And now b tilde lives in the context gamma equal a tripled. So now to instantiate,
Why, sorry, here again, let's do it together from two sides of the
okay,
why gamma equal here? Why not gamma?
because it's my rule is because this equality is heterogeneous, I have to triple all my assumptions one after the other. I mean, if it's just one assumption, like in the vector example, I just need one equality proof. But if
Because
I-
equality on A is also heterogeneous.
yes,
So you
Of
don't,
course.
you wouldn't kind of need it, but, I mean,
It depends.
originally you don't need it.
but it could happen, right? When I define something on vectors, a type which uses these vectors again, then I have two dependencies. The first dependency on the natural number, and then the dependency on the vector, and so on. So that can be iterated. Yeah.
What context does tilde B live in?
Tilde b, then since b lives in the context gamma x colon a, tilde b lives in the context gamma
gamma
x colon A equals, which I have expanded here. Right?
Why don't you have to put B into the context to get?
So B is the type, right? In the context gamma x colon A, B is the type.
Oh, I see. So the bracket 0 is serving two purposes. On the one hand, A bracket 0 is a variable, and on the other hand, B bracket 0 means some sort of substitution.
No, I think you're misreading. His substitutions are coming in from the left, so it's not substituting into B, it's substituting into B prime.
Substitution into tilde B. This is
That's
substitution.
tilde B by
tilde
itself.
B.
Sorry? Yeah.
No, it's on the right. It's substitution. It's exactly like in categories with families when one writes x of f or a of f.
That substitution you have there
Is
is
operating
acting
on
on
B.
B prime,
It's
on
operating
B
on
or
B
on tilde
prime.
B.
So we're having tilde B.
It acts on tilde B.
Okay, thank
Read
you.
it like this. It acts on tilde B.
That's what needs to be explained.
Yeah. Thank you. Okay. Maybe I'll do another slide since everybody is confused by this one.
Well, let's.
Okay, the one remark, I shouldn't leave the slide on any longer, but anyway, that in the moment we are going to give a trivial interpretation of equality in the universe. We just say equality in the universe is any relation between these two types. And this is what you need for this parametricity interpretation. But later, we're going to replace this by what we really want, namely that there's equivalence between these types. But it's good to do this in stages. And first of all, look at this parametric interpretation. So, one important remark is that this operation, tilde equal, equal on context, actually.
Wait.
Sorry? Yeah.
Can you, what was the sequence of the slides?
This is the first slide,
Okay.
then the slide after, and then this is the slide to which I wanted to go now.
There's a number in the lower right.
Yeah, that's what I'm like.
And I think you put the numbers in order.
Actually, I think I haven't explained that. Maybe I shouldn't spend time on this. No, it comes later. Okay, sorry. So there is an action. There are two things. There is an action on substitutions, but there's also, maybe let's look first on this operation, which says that every term preserves equality. So if I have a term of type A, then I have the substitution 0 and 1, which means I can lift t into gamma equal. So t0 is only depending on the first part of the context, and t1 only depends on the second part of the context. And now I want to say that every term preserves equality. This is sort of what you call resp or con in type theory. And this is defined by recursion over t. T star is a proof that t0 is equal to t1. So this depends on all these equality assumptions here. And it says that t is then a congruence. And this again can be defined in a quite obvious way by recursion. If you just look at application, for example, if you construct f star, and if you remember now that pi types now take 3 arguments, 1 and 0, 1 and 1, and that is proof, so we just have to expand it like this, and matchingly, lambda abstraction also gets now 3 assumption, x0, x1, and the proof that these two are related, and then we recur to t star. And the base case is how do we translate variables, and we translate variables just as x2, and how do we translate the universe? So here we just use the definition of equality of the universe, which matches exactly what we need at this point.
Thorsten,
Yeah.
So example, like almost right away, you're looking at equality between equalizers, right?
Yeah, but that's automatically, because every equality is defined as a type, right? So previously, I gave an explanation which eliminates equality Yeah, equality of a pi type is a pi type, equality of a sigma type is a sigma type, and equality in the universe is just this thing. So by applying this, I can always eliminate any equality until I run on a variable, as was already remarked. Yeah.
Okay.
But what actually do you do when you use a neutral type expression? You don't do anything.
Nothing. I mean, like, as I say, for plus x, y, you just wait and hope that somebody will instantiate the variable, and then the computation continues.
And if you have a context of length n, then how many terms are in gamma equal?
3 times, I mean, 3 times the length, 3n. So gamma equals,
3n or something like 3 to the n?
no, 1 equals is 3n, but you may do equals, you may have to do equals lots of time. When you ask this question, what is the equality between the equalities, then you repeat your equals construction.
But I mean, if I have a1 in x1, I do equals to that, I get a1 plus in x1, a1 minus in x1, and a1 tilde in between.
I mean, if you just look at this slide, about each assumption here,
But then if I have a second one, I would need to.
I think the terms will get complicated, but the number of things in the context is But when you have equalities of equalities, that's going to be horribly complicated when you actually unfold.
then you repeat this equality construction. So oh,
Yeah, we shall see. Yeah, it's still fine. I think I will use the whiteboard as well. So, yeah, so this heterogeneous equality that Thorsten defined before was living in this extended context. So, in order to talk about equalities of elements of A, we had to go up one context. So this is why it was more external parametricity. We can only reason about it externally. It's in a different context. But if we want to have the usual equality, which lives in the same context, between the same types, like this, we need to do something, and this is when we start to internalize this equality. So we do this by adding a substitution, which goes the other way, from gamma to gamma equals, which just repeats. So the two copies of the same type, we just put in the same variable there. And then we add this new raffle construction there as the connecting, or as the line between those 2 points. And this raffle of x will be a new normal form. So if x is a variable. So this is something, an additional term that we added into the type theory. So far we just, like, all the operations that we defined could have been viewed as meta operations, and now we add something new. And we also add the computation rule for raffle. So if A is not a variable, then we can compute further. We just use this star operation and then apply this R substitution, which duplicates the elements. So this is how we define this homogeneous equality, and we just abbreviate equals on A by this construction. So here again, this R substitution is applied to tilde A, to this relation. Okay. So yeah, so gamma equals can be viewed as the context of as a duplication of this context gamma, and proves that the duplications are pairwise equal. and this 0 and 1 project out of the one part or the other part, and R just duplicates everything. So if we go R and then 0, it's the identity substitution. Or R and 1, R composed by 1 is also the identity substitution. Okay. Oh yeah, so we added this new normal form, raffle X. So now we need to extend our star operation because we didn't tell how star should act on raffle. So we need to make a choice of what raffle X star should be, and we already have raffle of X star. We could just that could be a natural idea to just define raffle of X star as raffle of X star. But these terms have different types. So if you unfold this complicated type, now this is a second. So there are two levels of equalities here because this is in the 1 times equal context, and then R, which is included in this construction, lifts even 1 higher. So we are at 2 dimensions. These are the types that we have. We don't need to understand it yet. So we just reflect on what we were doing and how this equals functor acts on context. So if we have a context with one element, context of points, and we apply this equals functor once, we get a context of lines. If we apply it again, we get a context of squares, and the filler, the last element is the filler here. And if we apply it again, then we get a context of cubes, and so on. So this is a very natural way how we end up having cubes. And these indices here just correspond to the position of the cube, in which dimension, position of the face of the cube, in which dimension, where that face lies. And this is nothing new, so this is just generated by our equals construction. We add new indices in the end at each level at each iteration of the equals functor. So when we view these two types of these two different raffles that we had before, with this in mind, then we see that this one raffle is a filler of one square, and the other raffle is a filler of another square. And these two squares are very similar to each other. They are just, the only difference is that their dimensions are swapped. So this is why they have different types. They contain the same information, but in a permuted way. So we wanted to define this star operation on raffle. That was the goal here. So this motivates us to define a new kind of substitution in addition to R, this S, which just permutes the dimensions of one square. So now S of X in A, it works in the 2 times equal context. So S of gamma goes from gamma 2 to gamma 2. So 2 means equals equals. And this is how it acts at the context. And this component here, this x22 applied to SXA, will become a new normal form again. So this S substitution here, it can be viewed as some additional structure on variables that we didn't have before. Or it's a similar additional structure as raffle was. So raffle of X was a new normal form, and now x22 of Sx is also a new normal form, and also this one is a new normal form. So first a raffle, R substitution, and then an S. But then we can go on and ask what the star of S is, and so on. So if we do this and look at the full picture, what's happening and how these things compose, then it turns out that this R and S and 0, 1 substitutions together with this equal context give the counterpart of the base category of the cubical set model. we define this R substitution for gamma, and it went from gamma to gamma equals. But now for the next dimension, there are two ways to live this R substitution. We can either apply it on gamma equals directly, and then we go from gamma equals to gamma 2, or we can have this substitution R gamma and then apply this equals on it. So here we apply the factoriality of equals, that we can apply it on substitutions as well, and it will have the same type. And in general, if we look at every dimension, if we have R gamma ij, it will go from gamma I plus j to gamma I plus j plus 1, and it will add the degenerate dimension at index I. And also similarly, we have S gamma from gamma 2 to gamma 2, and there are also that many ways of lifting this S gamma substitution. So in general, if we have S gamma ij, it will go from gamma I plus j plus 2 to gamma I plus j plus 2, and it will swap the ith and the j's dimensions of the cube. This is how it acts. And with this in mind, we have we can and then there are many laws between these substitutions. So for one that I mentioned was that if I do R and then 1, it's the identity substitution. Or if I do R gamma equals and then I swap the dimensions, it's the same as adding a degenerate dimension at the other coordinate, at the other dimension. So by using these rules, we end up with these normal forms. So it's these R gammas. So first we add k times a degenerate dimension at the end. So always as a last dimension we add a new degenerate dimension, and then we swap. We do some swaps. Yeah. So this is basically a degeneracy. So it corresponds to an Eilenberg triple in the simplicial model. So and this is this additional structure that we have on variables. So a last element of a cube can be this one if it's a variable and it hasn't been and the substitution hasn't been applied yet. So no computation has been done yet. Okay. Yeah. So how do we apply a substitution to these? So we have another law for R's. This is the naturality law. We think about the model. So R gamma is the same as R rho is the same as rho equals R, and with the help of this law, we can just lift. If we have such an X, we can just list the substitution rho from back to front until the S's. So we can just then in the end we get rho to the k. So k times equal version of the rho, and yeah, and now we somehow need to explain how to swap these dimensions, and then if we are able to put rho somewhere here, then the components can be read out from this rho, and we can compute further. But as of now, this is stuck, and we can compute further by doing another recursion on types. So as an example for the non-dependent pi type, if we apply the star operation or the tilde operation twice, this was a question: how do we do higher equalities? So, for example, higher equality for a pi type is just it computes to this. So it's a relation from all the so it's a relation from x in A2, which is a context of 9 elements. So it's a square of A, and it returns a B star star, which is a filler of a cube which has type filler of a square which has type B. Okay, and
Wait a minute.
sorry.
So you have an arrow,
Yeah.
and to the left of the arrow is a context.
Yeah. So this is this. In fact, I mean a big pi type which has all these elements. This is an abbreviation for that pi type. Yeah. So
It's
this is
active.
informal.
Also, the
No, not really. No,
Well,
this is not. So x colon a2 means this. So x colon a2 r of b star star is the same as a big pi, which has 9 components and it returns a b star star. And the 9 components are x0, 0 in a0, 0, x0, 1 in a0, 1, and so on. So it's a square, where x22 is the filler, this is x00, x10, and so on. So this is just an abbreviation for this. And this generalizes to all higher levels. And if we know that this f function, this f variable has a function type, we are able to here we just and then we apply this substitution. So our goal was to commute this substitution s with another substitution rho. So this is how we do it. We eta expand this function. So now this is what we get. So this s is again applied to this function, but then instead of applying this to the function, this substitution to the function, what we can do is first I swap all the arguments of the function here, then I apply the function to these swapped arguments, and then I swap the result again. And I had to swap, and now instead of swapping a r o b, I need to swap a, and then I need to swap b. And in the end, I end up with a base type, and for base types I don't need to do anything. I don't need to swap. So this is how I can compute. And I mean, this is the most subtle part of this internal parametricity work by Moulin. And the next step is to replace this definition of tilde u, which was just a relation space, with equivalence. And we need a form of equivalence which includes a relation to be compatible with the previous setup, and it's this form of equivalence. It's also in the Homotopy type theory book, and our long version is just expansion of this form. And this expanded form basically says the following. So if I have a type A and a type B, and I want to then I have a relation tilde e between them, okay, or here I just call it tilde. Then if I have an element in A, so this x0 is in A, then I need to be able to coerce it into B, and this line will be called coherence of x0. These are the first two components here. And uncoerce and uncoherence mean that if I have another, sorry, it was called x, so let me just call it x. And if I have another, if I have an x and a y, and they are connected by p, then I have a square like this. So this is just reflexivity, and this is called uncoer, and this is called unco. So this means that I can, instead of just having a relation, I have a way of transporting from one type to the other, this coerce. I know that transportation respects that relation, which is co, and I also know that it is unique. So whenever I have another y, then it is equal to this coerce x, and by this uncoerce, these are in the same type. But and also the coherence is equal to p, which is a heterogeneous equality. That's why I need a square here, because these co x and the p have different types. This is co x on the right hand side, and this is y. So this is how my definition of equivalence. And now we
Question?
yeah.
some of these tildes you left out some subscripts, correct?
Yeah, so these tildes here just refer to that tilde, to the first component. Yeah.
The last line, that xy should be. No,
Oh yeah, so this is and rho is an abbreviation of some
the
long
last line would
expression.
be lower there.
Here,
That would be the last line, yes. So are there, the tilde there?
it refers
Is
to
that
this tilde.
Ah, okay, yes, yes.
And this is also.
Sure.
So the course and coherence give me the center of the contraction, and these connect everything else to the center of contraction, this uniqueness condition. Okay, so now I replace the definition, this definition of tilde u. So now I need to do some more work, because previously for each type A, I said each type, yeah. So a type A, I defined A star, and A star was just tilde A. So for a type, I only had to provide one relation. Now instead of just providing one relation, I also need to provide this coerce, this coherence, and also these uncoerce and uncoherence. Yeah. So for example, and I need to do this work. So for example, if A is the universe, then I need to say what course in the universe is. So I have one type A0 in the universe, I need to give another type which is also in the universe, and I just give the same type. And they will be connected by this tuple, which has 5 elements corresponding to the 5 elements of the universe, the relation, coherence, and coerce, coherence, uncoerce, uncoherence. And for the universe, these are basically just reflexivity, identity functions and reflexivities of these other components that we already defined for the other type. So for example, this uncoerce of A star has to be defined for A star, whatever A star was. And then we apply this R function, and this is how we do this. Yeah.
But there is
Okay.
only in one direction. You have to.
Oh yeah, sorry. Yeah. So here I only showed this construction for one direction. Yeah. So there are 2 components, and these are one direction, and these go the other direction. I didn't expand the full thing, and also here for this definition, I only included this direction and not the other one. Yeah. But we do both at the same time. Okay, and another example, the coerce for pi works like this. So I have a function which is pi x in a b 0, and I need to provide a coerce function, a coerce of this f, which lives in pi x in a b 1. So what I do is I first take the argument, which is in a1, and coerce it back into a0, and then I will be able to apply the function. And then after I apply the function, I coerce it forward now in b, and I get my result in b1. Okay, and in fact here this b depends on this square. So you can imagine a substitution here as well, similarly as for sigma, which includes this for x0, this for x1, and this for x2. So b is a dependent type. And for the coherence, I need to go. Yeah. So this coerce and coherence can be viewed as first level Kahn conditions. So if I have a point, I get another point and a line connecting them. But when I want the coherence for functions, I need to go one level up. I cannot just use the coerce and coherence already defined, but I go one level up and use I need to somehow get these higher level these second level Kahn-filling conditions. So,
It's like, it's a trick.
Okay. This is when, I need to get. Yeah. So.
We because that was a question which I was kind of trying to understand. So how come you don't need the cancelling conditions, and so now the cancelling conditions seem to
Yes,
have
yes.
appeared. And so could you just again sort of point out where was the first time where it appeared?
Yeah.
And so you're saying it's this which you called COH, Koch.
Yeah.
Why was it needed?
I needed it in the definition of the universe. The definition of equality for the universe. So in the definition of equivalence, I included the first level can-filling conditions together with a uniqueness condition.
What could you not have?
No, I need this. So I use this definition of equivalence, and this
Okay.
includes first level can-filling conditions. Yes.
I mean, once the equality in the universe is equivalent,
Yes.
so then we cannot just leave out something because it's not equivalent.
Okay. Well, I would probably need to look at the proposal more.
I mean, the Bible says that this relation is 1-to-1 in a homotopical setting. I mean, if everything is propositional, then it means for all x there exists exactly one y, and for every y exists exactly one x. Instead, you say that the pair is contractible, right?
Yes. Okay. I was actually.
And the stuff above is just the unfolding of this, what it means is contractible. This is center of the contraction, and so on.
Okay. And then the second.
And then here we would need the second level can-filling condition, but we don't have it because we only have the first level. Yeah? So I don't tell all the details of this, but it's in the cubical set model you also need to go one dimension up to do the can-filling for pi. So, but it turns out that some of the higher can conditions can be derived from the first level can conditions in the universe. Because if we look at this type, this x0 tilde x1, it is in this context. Gamma equals, and I have x0 in A0 and x1 in A1. And now this is just a type in this context, so I can star it. And then I will have this element in this extended context. So what is this extended context? It is gamma equals together with this line and this line. So the two sides of this square, the two vertical sides of this square. And this says that the type of these lines connecting x0 to x00 to x10 are equal in the universe to the type of those lines x01, x11 in the universe. So in particular, we also get a coherence function from this type to this type, which is just, and the coherence, which is just the filler for horns of these forms. And also we can fill the other direction because we also get a coherence and coherence from this type to this type. So this particular can filler is a special case of a first level can filler for the universe, but for a higher type. Okay. And with the help of this, I am able to define this this filling here, because it just goes the same direction. And I also needed filler in this direction, but that's just the uniqueness condition for the other direction. So it doesn't feel this. It's like this. It's like a filler for this horn, but it goes in the other direction. Yeah? So it turns out that without adding any higher can fillers, we get all we need for pi types. Yeah, and so there's one thing that I'm not talking about here, which is the most subtle part of this construction, is that just as I had to do some tricks to compute these swaps for any type here, so for pi types I had to do this trick to commute substitutions with the swaps. I also need to do a similar construction for the new universe that I had now, because I replaced the definition of the universe. And in that construction I need to compute a Kahn filler for this horn out of a Kahn filler for this horn, for example. So if I have a filling in this direction, or the structure that I have here, I need to compute fillers for such horns as well. Because if I swap the universe itself, then the universe contains a filling in this dimension, this direction that I just showed you. But I also need a filling in the, but when I swap it, this is what I will get, because I just swapped the dimension. So I need to compute this one. And so this is the part which corresponds to the proof of the universe being Kahn in the cubical set model. But yeah, but my time is over, so maybe I won't show you this step here. And yeah, we can also derive the eliminator for the identity type. Yeah, so here the non-dependent eliminator will be just a coerce function for the predicate P, or for the family of type P. So P star substituted by R says that if I have two equal elements in A, I will get two equal elements when I apply P to them in the universe. And in this universe, I can coerce from this type to this type. So this is how I just define this transport function by the coerce of this P star R gamma. Yeah. So in this talk, Thorsten, we showed a different presentation of internal parametricity with this explicit substitution calculus, and what the connection of it is with the cubical set model. And then the basic step, the combination of the cubical set model and the internal parametricity work was to replace the definition of the of tilde u from relation space to equivalence. And this forced us to define the first level Kahn operations for every time. Yeah, this is not completely true, because not all the higher level Kahn operations are first level Kahn operations for a higher type, but some of them, and the others are hopefully definable. So this part is not completely finished. So hopefully definable by other means. And I haven't showed the how to do. So I had to and don't only have to define the course and coherence for pi and all the type formers, but also these uniqueness conditions. I haven't showed this, and currently we are working on an implementation of this in Haskell. This parametricity, the internal parametricity part is almost finished. And there are some questions: how shall we do higher inductive types, and whether we get the definitional computational rule for the identity type. This equals functor, if it's also a monad, it seems then that we get these connections, these connected cubical sets. So that's the additional operations that we need to define for that. Yeah, so that's all I wanted to say.
Coming back to your original question, I've lost the thread a bit. What is the answer to the original question?
So, when this is all finished, we have a type theory where univalence is the equality between
Sorry, but
Sorry, but one more word, yeah.
okay.
And we have
Yeah,
the usual constants associated with the equality type, so reflexivity and J, which are now not really play a different role. I mean, they're really derived from these more basic combinators.
Right, but I'm thinking more from a user point of view.
Okay.
So I'm a user, I'm doing ordinary type theory, I postulate univalence.
Yes, we don't.
But now, can I then have that zapped into your type theory without knowing much about it and have it reduced?
Yeah,
as it were?
that's the idea. Yeah.
So
So everything computes. So everything here computes. All the natural numbers, all the programs run. I mean, this is always a bit of the current state.
so I'm not going to need to see in triplicate myself.
No, we don't need special glasses.
Yeah. So good. That's good.
However, I mean, it's possible to hide all the structure, but it may be useful not to do this. There may be some things you want to do exploiting the structure. So that's not clear in the moment. I mean, you could just package it up under the surface and just say, okay, it looks like ordinary type theory, but behind the curtains, exciting things are happening. But maybe there's more you can do with this construction than just implementing the usual combinators we call it.
Well, of course, we mathematicians will want to see the whole thing.
Yeah.
So we shouldn't.
Is there a model in consimplicial sets that demonstrates consistency?
I mean, this type theory is closely associated to this cubical set model. So it's sort of it's sort of the theory or the classifying syntax for the cubical set model.
But you can repeat the same question. Is there an obvious model in cubical sets for this theory?
Yes, so the syntax itself is a cubical set.
But that, I don't see how that answers the question, because, for example, the syntax of ordinary type theory is globular, and yet we don't have a model in globular sets. There's a simplicial model and there's a cubical model. So to me, the relationship between just having a syntax of one shape and a model in another shape is unclear at best. That's why I'm just curious if I mean, maybe it's obvious here, but
Well, for this guy, it's not very clear what the model is.
right, that's true.
So, because it's not the same as a type theory in the sense of kind of Martin Luther. It doesn't fit into this contextual category, where I don't see how to build a contextual category out of it. Right? I mean, the starting point of any semantics is to build a contextual category, and then from the contextual category, by relaxing various things, to move towards something more mathematical. But here I don't see, I don't understand what the first step would be. Is there?
Okay, I mean, I think the idea should be somehow everything which is true in all cubical set models, or I mean, should be derivable in the syntax. So the syntax tells you what holds in the cubical set. In the Kahn in the Kahn substructure of the cubical sets.
How does that relate to whether it's consistent?
Because the cubical set model is consistent.
So what you said is everything provable in the cubical set model should be provable here. You want to show certain things are not provable, such as false.
Okay, well, maybe more precisely, everything is an if and only if, so that would be the conjecture that this system models exactly what is provable in all cubical set interpretations. But I mean, that's just
The cubical set interpretations are these non-existent models that Vladimir said wasn't clear.
one.
Cubical.
So use that.
We can speak in respect to one model, or we can respect
So this
respect to our notional model.
Yeah, we can
consistency effect.
Or we can have
Okay.
D.
The other line.
Okay, we do know what
Yes,
substitution is.
that sounds like sounds like an exciting alternative.
No, just do the semantics over the derivation.
I think that's how we clarify the situation.
So